Welcome to Unit 6, Day 2, Triangles and Trigonometry. Trigonometry is used to calculate the length of sides and the measure of angles in triangles. This entire unit deals with right-angled triangles. Right-angled triangles are the triangles with a 90-degree angle on them. The three sides of a right-angled triangle are the hypotenuse. It is the side across from the right angle. It's the longest side in every case. Adjacent, it is the side closest to the reference angle. It touches it. And opposite, it's the side across from the reference angle. So here we have a triangle, XYZ, and we're being asked to identify the hypotenuse, the adjacent side, and the opposite side for angle X. Angle X is what we refer to as the reference angle. All things will be relative to this specific angle. So the hypotenuse is always the angle across from the right angle. No exceptions. The opposite side is the side directly across from the reference angle. And the adjacent side is the side that's right next to the reference angle, but not the hypotenuse. Opposite and adjacent sides of a triangle change depending on the location of the reference angle in the triangle. So here we have XYZ. We're told to begin with that the reference angle is Z. Again, the hypotenuse is always directly across from the right angle. The opposite side is always directly across or opposite the reference angle. And the adjacent side is always next to the reference angle, Z in this case. But we're told that the opposite and adjacent sides of a triangle can change depending on the location of the reference angle in the triangle. Now, to begin with, we're told the reference angle is Z. But what if the question decided, or we decided, that the reference angle would suddenly become X instead? Now, the opposite side is located down here, and the adjacent side is right here. Let's change our reference angle back. Our adjacent is here, and our opposite is here. Let's change the reference angle to X. And our opposite angle changes as well, as does our adjacent. Notice that the hypotenuse side does not change. It always remains directly across from the right angle. Here's another example. Again, the hypotenuse is always directly across from the right angle. First, we'll establish our reference angle. We're told that the reference angle is R. Now our hypotenuse is directly across from the right angle. Our opposite side is directly across or opposite the reference angle. And our adjacent side is right next to the reference angle. Next example. Our reference angle, we're told, in this case, is L. The hypotenuse is always directly across from the right angle. The opposite side is directly opposite or across from the reference angle. And the adjacent side is right next to and touching the reference angle. In this example, we're told that our reference angle is F. The hypotenuse is directly across from the right angle. The opposite side is directly opposite across from the reference angle. And the adjacent is next to and touching the reference angle. Every right-angled triangle has specific ratios related to the measure of the acute angles and the lengths of the side of the triangle. These are called trigonometric ratios. These ratios are used to find the length of a side or the measure of an angle. Now that's a lot of information, and without really any examples, a little bit difficult for us to figure out. So let's carry on with that. We'll circle around back to these definitions, and hopefully they will make more sense. So these trigonometric ratios are called sine, cosine, and tangent. These mean that the sine of any angle is equal to the length of the opposite side divided by the length of the hypotenuse side. It also means that the cosine of any angle is equal to the length of any adjacent side divided by the length of the hypotenuse side. It also means that the tangent of any angle is equal to the length of the opposite side divided by the length of the adjacent side. And this page is basically restating the same things, just in a slightly different manner. Now this acronym, recalling that the sine is equal to the opposite over the hypotenuse. If we look right here, and the cosine is equal to the adjacent over the hypotenuse, and the tangent is equal to the opposite over the adjacent side. A little memory aid or mnemonic is SOHCAHTOA, which basically sums up this information. One last little bit of a definition before we go on to more concrete examples. We will sometimes use the symbol theta to represent angles. Okay, something a little bit more concrete that hopefully will help us make sense of all of those symbols and definitions. We have a reference angle of 53 degrees. It's the reference angle because the question tells us that it's the reference angle. So we're told that the reference angle is 53 degrees. This side is 4. This side is 5. And this side is 3. We're also told that this angle A is a 90-degree angle. This is a right angle triangles. All the triangles that we'll use in this unit will be right angle or 90-degree angle triangles. So what the trig ratios tell us is the sine of 53, sine of theta or sine of 53, is equal to opposite over hypotenuse. So sine of 53 equals opposite 4 over hypotenuse. In this case, we can state that the sine of 53 is equal to 4 over 5. We can say that the cos of 53, or the cosine of 53, is 3 over 5. Why can we say that? Cosine is adjacent over hypotenuse. Here's our reference angle. Adjacent is 3, hypotenuse is 5. So the cosine of 53 is 3 over 5, which we've stated up here. Now the tangent of a sine is the opposite over the adjacent. Here's a reference angle. Here's our opposite, 4 over adjacent. So the tangent of our reference angle 53 equals 4 over 3. We can calculate the sine, cosine, and tangents and see if they are the same as the fractions. We'll need to use a calculator with scientific functions with the sine, cosine, and tangent functions in order to figure this out. In this particular example, we're asked to figure out the sine of 40 degrees, sine of 50 degrees, cosine of 40 degrees, and so on. So, to figure out the sine of 40 degrees, we type in this calculator, 40, we go up to our trigonometry section, and then we click sine. And when we do that, we'll get an answer of 0.6243. We follow the same steps with these other examples. We type in 50, then the sine button, and that will give us a value of 0.766. In example B, the cosine of 40, we type in a 40, and then press the cosine button to give us 0.766. The cosine of 50, we type in 50, and then we get a value of 0.643. For C, we type in a 40, and then type the tangent button, or click the tangent button, and get 0.839. And then for the final one, we type in a 50, and then the tangent button, and get 1.192. Now, different calculators have different ways of doing this. For some calculators, you might have to press the sine or the cosine or the tangent button first, and then put in the angle. For this particular calculator, you type in the angle first, and then type in the trig function. We notice we have a little pattern right here. 0.6243. Cosine of 50 is 0.643. 0.766. 0.766. Carrying on to the next example. Which location you calculate depends on the information given in the triangle and the location of the angle. Here we're given a reference angle of C, and then we're given these two sides. These two sides happen to be the opposite and the hypotenuse. So we're given the opposite and the hypotenuse, and then we look up to our chart and ask ourselves which of the trig ratios allows us to get an answer with opposite and hypotenuse. Well, the sine trig ratio gives us sine of theta equals opposite over hypotenuse. So we're going to use the sine trig function. So we can write in, once we've established it's going to be sine, we can write in what our opposite and hypotenuse values are relative to angle C. So sine C equals 4 over 6, because relative to the reference angle C, 4 is the opposite and 6 is the hypotenuse. 4 over 6 can be expressed as a decimal, 0.667. In this example, we're told that our reference angle is L. This little semicircle here is this particular question's way of indicating what the reference angle is. So, our reference angle is L. What are we given? What do we know? Well, we don't know the hypotenuse, but we do know the opposite, and we do know the adjacent. So if we know the opposite and the adjacent, we can look down here and see that opposite and adjacent works with the tan trig ratio. So using that tan function, we can say that tan of L, or tan of theta, equals opposite over adjacent. So tan of L equals 9 over 8. 9 is the opposite, 8 is the adjacent. 9 over 8 can be expressed as 1.125. So we can finish off by saying tan of angle L equals 1.125. In this example, we're told that our reference angle is X. Now we look at what we're given. In reference or relative to angle X, we know the opposite and we know the hypotenuse. The opposite and the hypotenuse works with the sine tangent. So we're going to use the sine tangent. Sorry, we're going to use the sine trig ratio to express our equation. So we would say sine theta equals opposite over hypotenuse, which means that sine x equals 3.2 over 11.5. over 11.5 can be expressed as a decimal. So our answer here is sine x equals 0.278. Yet another example. So we're asked to write a ratio comparing the length of side opposite angle F to the length of the hypotenuse. Then express the ratio as a decimal rounded to 3 decimals. Which ratio does this correspond to? Well, our reference is F, and we're being given the opposite side, and we're being given the hypotenuse. So we have to ask ourselves, what ratio or trig function works with opposite and hypotenuse, and it just so happens that it's the sine ratio. So we could say the sine of f equals opposite over hypotenuse. Using our numbers, we can restate that as sine of f equals 2 over 5. Two over 5 can be expressed as a decimal 0.4, so we can say sine f equals 0.4. Now we're going to do the same thing for the cos, the cosine, and the tangent functions. So once again, our reference is angle f. So we could say that the cosine of f is equal to adjacent over hypotenuse. So in this example, the cosine of f will be equal to 4 over 5. 4 is the adjacent, 5 is the hypotenuse. 4 over 5 can be expressed as a decimal, so we can say the cosine of f equals 0.8. We can also express a tangent ratio. The tangent is the opposite over the adjacent. So the opposite of f is 2, and the adjacent of f is 4. So we could say tan f equals 2 over 4. 2 over 4 can be expressed as a decimal, 0.5, so we can also state that tan f equals 0.5.